Alright, so now we are ready to start solving the exercises of this section. In this first one, we are given two nilpotent linear transformations S and T, and they commute with each other. St is equal to Ts. Then we have to prove that their product St and their sum S plus T are also nilpotent linear transformations. So let's see the solution. Since S and T are nilpotent, so S to the power m is 0 and T to the power n is 0 for some natural numbers m and n. That means positive integers m and n, because that's what being nilpotent means, that some such power of the operator becomes equal to the zero operator, zero transformation. Alright, now we can assume without loss of generality that m is greater than or equal to n. This of course we can assume. Now our aim is to show that, say first, St is nilpotent. So some power of St where the exponent is a positive integer should also be equal to 0. And this is where we are going to immediately use the fact that S and T commute. Okay. Now, since S and T commute, we have this. What will happen if we consider the mth power of St? Because they commute, this will be equal to this product. In general, this is not possible. In general, St to the power m means St times St times St, m copies of St get multiplied, and that's not necessarily this, but because they commute, that's why ultimately you can bring, using the commutativity property, all the S's together and all the T's together, and that's how you get S to the power m times T to the power n. Alright. Now, what is, well, actually this part also was not really necessary. Yeah, this part is okay. Now only I am noticing this. I was thinking that we would need to assume that one of them is greater than or equal to the other. Yeah, so instead of erasing this part, I am just simply, without making a mess, I am just simply saying that there is no need to write this part. Okay, you straight away simply consider the mth power of St. Why is that enough for us? Well, that's because the mth power of S is equal to 0. So whether m be greater than or equal to n or less than n, it's not really going to matter. That's because now this is equal to 0. That's it. That proves that St is nilpotent. However, you still need the fact that S and T commute. Okay, that you need. Only this part is unnecessary. Next, we have to prove that the sum is also nilpotent. Now here, however, the exponent we have to choose a little carefully. We cannot just simply take m or n and expect it to work. Again, the fact that S and T commute will be useful here as well. Again, since S and T commute, it follows from the binomial theorem. I am putting a star here, that S plus T to the power m plus n is equal to summation m plus n choose, say I call it j, the binomial coefficient where j varies from 0 to m plus n times s to the power j times t to the power m plus n minus j. Okay. Now, what is this star? Well, you know that this is not the standard binomial theorem that you have in the system of real numbers or in the system of complex numbers, where say you expand a plus b to the power n, where a and b are real numbers or complex numbers. It's not that. Then what is it? This is the binomial theorem in a ring. Our operators are in that operator algebra, right? And that is after all a ring. And in a general ring, you do not have this binomial theorem. However, the objects, the ring elements, if they commute, then you have binomial theorem. And the form of the theorem is exactly like the one you have, the standard one. So that is why here also we need S and T to commute. Otherwise, there is also a general form of the binomial theorem in any ring. But because S and T are commuting, ultimately the form comes down to this familiar form. And the binomial coefficients appear as they appear in the standard binomial theorem. Alright. So that is why I have put a star here. This is not the standard binomial theorem, but the version of binomial theorem in a ring when the objects, the ring elements commute. Okay. Now we need to figure out that this actually will be equal to 0. Now here we can see that there are powers of s, s to the power j, where j is varying, and powers of t as well. Now, what is the power of s that will make what is the power of s, minimum power of s that is equal to 0? The minimum power of s that is equal to 0 may not be s to the power n. Maybe some smaller power of s also becomes equal to 0. But we need not worry. If our j, the j that you see here, if j is greater than or equal to m, then s to the power j will be 0. Let's write in details why. Now, if j is greater than or equal to m, j in this context, okay, j lies between 0 and m plus n inclusive. In that context, if j is greater than or equal to m, then s to the power j is equal to s to the power m times s to the power j minus m is equal to 0 times s to the power j minus m, so that is equal to 0. However, another question arises. Is this justified? We seem to have used one of the rules of exponents. Yes, this is justified. In a general ring also, you can have the rules of exponents, provided the objects that you see here make sense. I mean, you see, in a general group, we have the rules of exponents without any restriction on the exponents. For example, if G is a group and you have two elements A and B in G, then for any integers m and n whatsoever, they may be positive, negative, anything can happen. We have these two rules of exponents, right? A to the power, oh, why did I take B? Only one element is enough to state the rules of exponent. This is one of the rules of exponents and this is the other one. So this is the one we have used here, but the operation is multiplication of operators, which is just function composition. So the operator algebra from where these operators are coming is not necessarily a group under multiplication. However, still this rule will work provided the exponents are all positive integers, or if our ring has a unit element, then the exponent is allowed to be 0 also. That's the case here. And that is why we needed this condition that j is greater than or equal to m, because then j minus m is non-negative, it can be 0 or it is positive, and m is already positive. That's why there is actually no problem. But it is not the rule of exponent in a group. No, this is not a group under multiplication. But anyway, we get this. So for these values of j, the corresponding terms in this sum will vanish. They will just be the 0 operator. However, but what about those values of j that are less than m? What will happen to those terms? On the other hand, if j is less than m, then zero is less than m minus j, subtracting j from both sides. Or now if you also add n to both sides, then you will get n is less than m plus n minus j. So luckily in these other cases, if j is less than m, then s to the power j may not be 0. We don't know. Maybe 0, may not be 0. But m plus n minus j, the exponent of t, has now become greater than n. Hence, similar to this calculation, m plus n minus j is equal to, so you can write this like this. Okay, and again, this is justified because j is less than m. So this exponent here is non-negative. Actually, it's positive, but this we know is 0. So this is equal to 0. This means that no matter what j here you consider, either this term is 0 or this term is 0, and that's why all the terms of this sum are equal to 0, and that is why the sum itself is 0. Hence, s plus t to the power m plus n is equal to 0. Finally, note that since m and n are positive integers, so their sum is also a positive integer. Thus, s plus t is nilpotent. Okay, so that's how we have proved that the product and the sum are both nilpotent. Now let's see the next exercise. The next exercise is this. By direct computation, show that the matrices, now I need to write the matrices, these are 4 by 4 matrices, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so this is one matrix, and the other matrix is just like that, but there is a difference. Zero, 0, 0, 1. We have a 1 here. These two matrices are not similar. We have to show that by direct computation, without using any result or anything, just using the definition of similarity, we have to prove that these are not similar. We will suppose that they are similar and then try to reach a contradiction. Suppose that the given matrices are similar, then by the definition of similarity, there exists a 4 by 4 matrix A, say whose entries are Aij, such that A times the first matrix times A inverse is equal to this. I should have actually mentioned that A is invertible. Let me do it here. A 4 by 4 invertible matrix. Invertible matrix A such that A times A inverse is equal to the other matrix. Or A times the first matrix is equal to this times A. Now all we have to do is we have to calculate these two products and see what consequence it has. I mean the equality has. Now, and for ease of calculation we will actually have to write A fully. Otherwise, I mean, I don't know about you, but I cannot multiply two matrices if I just simply see one of them as just a name A. I need to have the entries. So let's first calculate this left hand side product. A11, A12, A13, A14, A21, 22, 23, 24, 31, 32, 33, 34, 41, 42, 43, 44. And I think it will be nice if we use ruler, otherwise it looks very messy. Zero, 1, 0, 0, 0, 0, 1, 0, and these two rows are entirely 0. Okay. And make sure you use square brackets and not leave just vertical bars. That will indicate determinant. You already know this. Okay. But I have seen many people simply they want to write a matrix, but they use square, vertical bar, ending up writing determinants and then continuing as if they are working with matrices. That's wrong. And if this is the problem, you can also use round brackets to enclose matrix entries. Okay, so now we are going to calculate the product. So let's do the calculation. First row times first column. Because the first column is entirely, it consists of only 0 entries. So the first row, first column entry of the product will be simply 0. then first row times second column, this times this times this times this. If you go like this, no, you can do it very quickly. Your left hand should go horizontally and the right hand should go vertically in sync. A11 times 1 plus A12 times 0 plus A13 times 0 plus A14 times 0. So that means A11. Next, first row, third column. This times 0, plus 0 plus 0. So this is A12. See, this times 0, this times 1, so A12. Then first row times fourth column is entirely 0, so 0. Now if you do similarly with the second row, the first entry of course will be 0 because the first column is 0. Then this times this. So A21. Next, so A22. And then this is 0 because the fourth column is 0. Do you see how fast this is? Well, of course, here so many entries are 0, that's why it is this fast. In general, it's not this fast. Then again, 0, 0. A31, A32. Like that. Oh, okay, now shall we get anything other than this pattern? The first and the fourth entries are of course 0 because of these 0 columns. A41, now same pattern. A42. So this is our product matrix, one of the product matrices. Okay. Also, now we are going to calculate the right hand side product. So here also write carefully 0 1 0 0 0 0 1 0 0 0 0 1. If you find this way of writing the entries of a general matrix somewhat cumbersome, A1 1 1 2 1 3, you can write letters here also, A B C D E, but then you will have to write many letters, and sometimes these double suffixes help you figure out some positional things, like for example where this entry comes from. So those things you can keep track of, okay, if you use this type of notation. A11 12 13 14 21 22 23 24 31 32 33 34 41 42 43 44. All right. Okay, what will happen this time? We have to write here. So let me write or I can write equality here itself. Again, 0, A21 and the other two are 0. So A21. 0, A22 the other two are 0. A22, 0, A23, then 0. Like that, 0, A24 and the other two are 0. Okay, so the job of the first row of this one is over. 0, 0, A31, 0. 0, 0, A32, 0. 0, 0, A33, 0. 0, 0, A34, 0. Then the third row, 0, 0, 0, A41. Like that, 0, 0, 0, A42. 0, 0, 0, A43. And finally 0, 0, 0, A44. And when you use the fourth row, everything will be 0 because everything is 0 in that row. So this is the matrix. Now from these two matrices and the supposition that they are equal, the corresponding entries should be equal. So what are we going to get? So we have the two matrices in front of us. This is one of them and this is the other. They are supposed to be equal. So what are the things that we are getting? Let us just simply write all the things. Okay. For example, A21 will be equal to 0. A22 will be equal to A11. We will figure out later which one of these equations are actually going to be useful to us. A23 equal to A12. Then A24 is equal to 0. Then A31 is 0. A32 is equal to A21. A33 is equal to A22. And A34 is 0. Then the third row, A41 is 0. A42 is A31. Then A43 is A32. Then A44 is 0. There is no point in writing 0 equal to 0, but this should be equal to this. So from there you get A41 equal to 0. Next A42 is equal to 0. And that's it. Okay, because the last one is simply 0 equal to 0. Now, can we say something from these equations about the matrix A? Well, you may notice some things. For example, this thing, A41 is equal to 0. A42 is also equal to 0. What about A43? Well, A43 is equal to A32. do we have A32 here? See, A32 is equal to A21 and A21 is 0. So you can see this one. A43 is equal to A32. Where is that? A32 is equal to A21. A21 is equal to 0. And something else also I noticed. What about A44? Yeah, A44 should be equal to 0. Where have I written this? Here. A44 is also equal to 0. So, we see that some of the equations ultimately we don't use. But that's not a problem because you cannot know everything beforehand. So now we write this observation. We note that A41 is equal to 0. A42 is also equal to 0. A43 is also 0, but that is not immediately seen. First, A43 is equal to A32. Then, A32 is equal to A21. And then A21 is equal to 0. And A44 is also equal to 0. So, the matrix A now looks like this. A21, 22, 23, 24. There is, it's not necessary to again write the matrix, but I just want to show it in the matrix form, what all these things ultimately mean. All the entries in the fourth row are 0. And that is a problem. Why? Because you know that when all the matrix, not just in the fourth row, in any row, all the entries in any row are equal to 0, that matrix cannot be invertible. We have, however, worked all these things based on the assumption that A is invertible. But this contradicts the hypothesis that A is invertible. And this contradiction, of course, arises from our supposition that the given matrices are similar, and that is why they cannot be similar. Thus, our supposition must be wrong, i.e., the given matrices are not similar. There are some little things that sometimes are overlooked and which make life hell. You may immediately, after making the supposition, you will write what it means for two matrices to be similar. A times one matrix times A inverse is equal to the other matrix. Now, if you just, without thinking much about anything, start writing what A inverse is, then everything will be unimaginably complicated. Not only will you have to write a very complicated matrix in place of A inverse, I mean, of course, if we are assuming that it's invertible, there is an expression for writing the inverse, somewhat complicated expression. What will you then do? You will multiply A and that matrix, and then you will have to multiply the result by that complicated inverse. This will make everything almost intractable, and it's unnecessary also. The smart thing to do is to take that A inverse to that other side, or to put it more accurately, multiply both sides from the right hand side by A. So that makes everything simple again. I mean, not that complicated. Still you have to do multiplication, but not that complicated. Okay, so that's how we have this exercise. So let me just end here itself. After this, there are many more exercises that we will solve in the next linear algebra video. And tomorrow, of course, we have our usual analysis. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.